The first 3 learning objectives we'll look at are explaining what the first law of thermodynamics is, defining work done, and we'll tell you what a closed system is as well, and then calculating the change in internal energy for a system undergoing a change in temperature or volume. All sounds rather tricky, but bear with me and we'll start from the very beginning. Talking about starting from the very beginning, I feel it's really important that we discuss what actually a thermodynamic system is. So let's go back to something we're familiar with. When we talked about work done in previous themes, I always encourage you to say, remember that work done is equal to the energy transferred. Well, when work is done, energy is transferred from one state to another. And doing work requires a source of energy. So if we want work to be done, we need a source of energy to make that happen. When we burn fuel, chemical energy is transferred into thermal energy. So that's our energy transfer here. We have an energy transfer and we want to do work with that energy transfer. But we need a system to allow us to do work. And that system in thermodynamics is called an engine. And introducing, in thermodynamics we call it the simple engine. And it could not be simpler. That's why it's called a simple engine. A simple engine is where an ideal gas is compressed by a piston in a cylinder. So this is our piston here. This is our cylinder. And this is our ideal gas. And it's usually monatomic as well. That means all the same types of atoms. Every single slide, practically, in this tutorial is going to use the concept of a simple engine. That's basically thermodynamics. So when we talk about an engine, we're talking about a cylinder which has got a piston. It's a movable piston. So this piston can go up or down. And it's got an ideal gas compressed within it. Why is a piston so interesting? Well, in real life, we can use this piston to do stuff, right? So if you imagine if this piston moves that way, then this rod moves that way, which means this joint moves that way, which means that this lever moves up the way. And if it moves forward, it moves along the way. And then when this piston moves backwards, this piston moves backwards, this joint moves backwards, and the system comes round. And what is caused by that is circular motion. Now, where would we find circular motion useful and pistons useful? In the olden days, it would have been a steam train, and in modern day time, it would be a petrol engine or a diesel engine. You can actually see in this picture of a steam train here, we've got pistons here. Those pistons are moving back and forth. When it moves forward, the arm and the lever moves this wheel forward. And when it moves backwards, it pulls this wheel backwards. So it's that rotational motion from the pistons that's allowing the steam train to operate. And of course, where are we getting that work done from the piston? Well, we're getting the work done from the chemical energy in the fuel. I don't know if you've seen images of train drivers in the olden days, but they would be shoveling coal into a furnace in here. And that chemical energy of the coal turns into thermal energy. And we take that thermal energy and the simple engine and we make this steam train go round. So that's why we care about the simple engine. That's why we care about a piston. And that's why we care about chemical energy in fuel turning into thermal energy. When we're looking at this piston, we're assuming that it's a closed system. A closed system means that no mass can be transferred in or out. So if there's a certain amount of molecules in here, all these molecules, they don't escape and no more molecules are injected in. The amount of gas within that simple engine remains constant. However, energy can travel in and out. It can be transferred in or out. It's just the mass of the system that has to stay constant. And now a closed system is different from an isolated system, because you've probably heard the phrase isolated system before. And an isolated system means that mass or energy can't be transferred. Whereas in a closed system, Mass cannot be transferred, but energy can. And it's really important that we can transfer heat energy in and out of this simple engine to make sure that that works. So when we're talking about thermodynamic systems and we're talking about simple engines, we're talking about a closed system. Let's think a little more about that transfer of chemical energy to heat energy and how we're doing work with that. In this piston, we have some gas. If we increase the temperature of that gas by adding a fuel and burning it, so we've got fuel here, that's supposed to be a flame, sorry. That's supposed to be a fire. But what we do is we add heat energy to it, okay? And by adding heat energy, we're going to increase the pressure of that gas. And by increasing the pressure, we're going to push this piston upwards. An expression for the pressure on this piston is pressure equals force over area. And if we rearrange it for force, then we have force equals pressure times area. Now, we know that work done is equal to force times distance. And instead of putting force in there, let's put this in there. So we've got work done is equal to pressure times area, which is our force, times distance. Wait a minute. Area times distance. Okay, so that's area times distance is going to give us volume. So instead of putting area times distance, we can have work done is equal to pressure times volume, or the change in volume. So when we have a simple engine, we can calculate the amount of work done by the gas in that simple engine by using the expression W equals pressure times the change in volume. That's when the gas is doing the work on the piston. The gas is heated up and is doing work on the piston. What about if we had it the other way around? What if we had a piston full of gas and we found a force and we pressed down that piston with a force? Then we'd be doing work on the gas. And when we do work on the gas, the work done on that closed system is taken to be negative. We now have an understanding of work done in a simple engine. I just want to do a quick recap of internal energy, which we studied in topic B3 gas laws. The internal energy of an ideal gas, and remember we're looking at an ideal gas here, is the sum of kinetic energies of the molecules in the ideal gas. So we've got all these molecules here. They all have a different amount of kinetic energy, and the total internal energy is the sum of the kinetic energies of those molecules. In B3, we came up with this expression for the internal energy of the molecules. It's related to the temperature because, of course, the kinetic energy of these molecules is directly proportional to the temperature. And this is the expression for internal energy. But if we want to find out what the change in internal energy is, well, R is a constant. We know that it's a closed system, so no exchange of mass. If there's no exchange of mass, then N is a constant. And 3/2 is obviously a constant. So if we want to find the change in internal energy, the only thing that would change is the temperature. So that gives us an expression for the change in internal energy of an ideal gas inside a simple engine. So what we have now is we've got work done for a simple engine, and we said that was W equals P delta V. And we've also got internal energy for a simple engine, and we've said that that is equal to delta U equals 3/2 nRΔT. Why do we care? Here's why we care. It's the first law of thermodynamics. By considering the law of conservation of energy, and of course we remember that as energy can neither be created nor destroyed, we can find that the amount of thermal energy or heat energy added to a gas must equal the work done by the gas plus the increase in internal energy delta U. And if we do that as an expression, then it's Q equals delta U plus W. of course, we had these expressions for delta U in the previous slide and an expression for W in the previous slide. So actually, the first law of thermodynamics, if you want the complicated version, is that. Most people just tend to rely on this though. Now we know the first law of thermodynamics, and I'll rewrite it here. We know that the first law of thermodynamics depends on the work done, and it also depends on the internal energy. Well, how can we tell what the gas is doing? If the gas changes in volume, so if this piston goes up or down, then that change in volume tells us that work is being done on the gas or work is being done by the gas. If work is being done by the gas, it's moving up the way. If work is being done on the gas, it's moving down the way. And because they are in opposite directions, we have work done on the gas is a negative and work done by the gas is a positive. We also know that the internal energy will increase or decrease depending on the change in temperature of this gas. So if the temperature increases, then we know that heat has been added. That means that the internal energy is positive. If internal energy decreases, that means that heat has been lost and the internal energy will be negative. If heat has been added, then the Q added to the system will be positive, and heat has been lost, then the Q removed from the system means that this will be a negative value. What I'd like you to do now is head to your revision note template and write down how work done is derived for a simple engine in the other notes section, which was, so show how we derived that. It was a very simple derivation. Then I went to go to the definition section and write it down, the definition of a closed system and the expressions for the first law of thermodynamics in the definitions section. Finally, head to the knowledge questions, which are downloadable below, and complete questions 1 to 4. In the learning objectives checklist, it then goes on to talk about the second law of thermodynamics, but I think it's better to leave that until the end of the tutorial. Right now, I'm going to base right on to something called isovolumetric, isobaric, isothermal and adiabatic processes, and we're going to look at them in a lot more detail. The basis of all these processes is something called a PV diagram, and this is not new to you. You've seen these PV diagrams in the previous topic in B3. These PV diagrams have pressure on the y-axis and volume on the x-axis, and when a gas undergoes a transformation from one state to another, these PV diagrams are really useful in mapping out that transformation. What's really interesting with a PV diagram is that we can work out work done from the PV diagram, because as we remember from before, work done is equal to pressure times the change in volume. And if we look at this first graph here, this length of the rectangle is pressure, this length of the rectangle is change in volume, and if you wanted to find out what the area of that rectangle is, you would do length times breadth, which is pressure times change in volume. What that tells us is that the area under a PV graph is equal to the work done by or on the gas. Now obviously in graph 1, finding the area under the curve would be very simple. It's actually just W equals P delta V. But for graph 2, it becomes a little tricky. It's not an easy, geometric shape for you to calculate the value of. So for this, you'd have to actually, which I hate doing, you'd have to count the squares underneath the graph and then work out the area doing that. I think it's highly unlikely you'd be asked to do that in an exam. I think it's too time consuming, but it's worth noting that you may have to count the squares underneath the graph to find the work done on or by a gas from the PV diagram. Okay, we're going to take our PV diagrams to the next level. First of all, let's ignore the term isobaric process. Let's ignore all the words. And notice that I've added some lines here. Do you remember what those lines are from the previous topic? They're isotherms. So any movement along these lines has the same temperature. We need to bear that in mind as we start to talk through all these different processes. Let's turn our attention back to the text, we're looking at an isobaric process. And an isobaric process is when a gas transforms from one state to another, but the pressure of the gas stays constant. Let's go to the PV diagram and see what that means. Let's give this a value. Let's say the pressure here is, 1 times 10 to the 5 pascals. That's a constant value of pressure. So if we want to do any transformation of the gas, it has to be along this constant pressure line. So if we have an isobaric process, you will see that the transformation line, is horizontal, meaning that the work done on or by the gas is a very simple calculation underneath that horizontal line. What else does it mean? Well, in this system, the transformation is going from right to left. That means it's going from a high temperature, because this is an isotherm for that temperature, to a lower temperature. So in this case, when we've got an isobaric process, we've got a temperature decrease. And that implies that the internal energy is decreasing, because delta U is equal to 3/2 nRΔT. If the temperature decreases, then the internal energy decreases. We can also see that the volume decreases as well. It goes from V2 down to D1. It's a smaller volume. And by a smaller volume, again, remember W equals P delta V. If the volume decreases, then we're looking at negative work. So if we apply the first law, Q equals delta U plus W, this tells us that Q is negative because Q equals minus delta U minus W. That's going to give us a minus value. So heat is lost in this system. When we're looking at the isobaric process, where it's going from a higher temperature to a lower temperature, kind of makes sense that heat is lost in this system. Now we'll look at the isovolumetric process. Guess what stays constant in this one? The volume. So we go back to our PV diagram and we want to keep a constant volume. That means we're going to go up and down. Tell me, is there anything to calculate underneath that line? Is there any area underneath that line? No, there's not. So that means that work equals P delta V. Well, delta V is equal to 0. So there's no work done when we have an isovolumetric process. However, what we do notice is, in this case, it's gone from a lower temperature up to a higher temperature because it's gone through the isotherms. So we can see that the temperature is increasing. That means delta U equals 3/2 nRΔT. That's increasing. So the internal energy of the system must be increasing as well. If we put that into the first law, Q is equal to delta U plus 0. So actually, when we've got an isovolumetric process, we can conclude that Q is positive if U is positive, if the change in U is positive. An isothermal process is where the temperature of the gas stays constant. And it's not a straight line here, because to keep the temperature constant, we have to stay on an isotherm, and these isotherms are curved. The temperature doesn't change. Remember what the expression for internal energy was. If this is equal to 0, because it doesn't change, then the change in internal energy is equal to 0. So when we're looking at an isothermal process, there's no change in internal energy. However, you can notice P₁, V2, there's a big change in volume. There is a change in volume. So we do have a positive change in work done. That means that when we go to Q is equal to delta U 0, our first law of thermodynamics, then the heat enables the gas to do work in an isothermal process. There's no change in internal energy. The final process is the adiabatic process, and it's one that's a little bit trickier. Now, the definition of an adiabatic process is when there is no exchange of thermal energy between the system and the surroundings. What does that mean when we're looking at our simple engine? Our simple engine, of course, is this piston. We've got gas in here. We give this gas in here energy, and we want the piston to do work. And usually what we do is we get the energy from the surroundings by burning fuel. In an adiabatic process, there's no heat from the outside. When that happens, the PV diagram looks slightly different. It goes from one isotherm to another, and it has a sort of curve to it. Okay, there's no exact science to it, but what we can see is that V1, V2, the volume increases. So that means that W equals P delta V. There's work done, and it's positive in this case. We can also see that this temperature 1 and temperature 2, that temperature 2 is less than temperature 1. So the temperature decreases. That means that there's a value of internal energy, which is, that gets smaller. The internal energy gets smaller, which is negative. So you can apply it to the first law, and you can see that the change in internal energy is equal to the work done. And that just means that the energy required for this gas to do work comes from its internal energy. There's no exchange of heat with the outside surroundings, and thermal energy has nothing to do in an adiabatic process. Let's take the PV diagram for an adiabatic process one step further. We talked about these isotherms earlier. They kind of got a funny shape. If you were a mathematician, you might be tempted to say that P is inversely proportional to V. It's not, all right? Because what you can see is that they're much more curved here than they are there. Actually, what the mathematical relationship is that P is inversely proportional to 1 over V to the power 5 over 3. You would never have got it in real life. Just trust me on that one. And by knowing this relationship, we can come up with an equation that allows us to calculate pressure and volume values between two states of gas. Because if we know that pressure is inversely proportional to V to the power 5 over 3, that means that P times volume to the power 5 over 3 is equal to a constant. Now, if it's equal to a constant in the first state, P₁V₁, is equal to a constant, the second state, P₂V₂, is equal to the same constant. And if they're equal to the same constant, we're able to get this expression up and running. So if you're looking at an adiabatic process, and again, an adiabatic process is one where no heat is exchanged between system and surroundings, then you can use this expression in your calculations. This expression only works if we have an ideal gas and a monatomic gas. Again, monatomic means all the molecules are the same. If we're using an ideal gas, of course, you might be asked to use this equation as well, because this is the ideal gas equation. So don't forget that stuff from B3. What I'd like you to do is, you've got a lot of graphs to draw right now. Head to your revision note template, draw the PD graphs for each thermodynamic system. Then I'd like you to go to the common formulae section, write down the adiabatic process expression, and in that case we're looking at P₁V₁ 5 over 3 equals P₂V₂ 5 over 3. And then head to your knowledge questions and do questions 5 to 7. In the last section, we talked about what happens when a gas goes from one state to another. In a steam engine, or a diesel engine, or a petrol engine, a gas goes from one state to another, to another, to another, to another, and it's a cyclical process. It goes round in a circle. And what we're going to do now is we're going to introduce the concept of a cyclical process and how that relates to engines in real life. And once we've got the idea of what an engine in real life, how it works, what the thermodynamics behind it is, we're going to look at the idea of thermal efficiency, and specifically a Carnot cycle. Cyclical processes. So a cyclical process is a series of transformations that take a gas back to its original state. And in this PV diagram, we've got a cyclical process shown. It's a very simplified one. We're going to start at position A. When the gas is in position A, we add heat to the gas, and you can see a process takes place. It's a process where the volume is constant. If the volume is constant, it's an isovolumetric process. And you can see that it goes through and up the isotherms. So we know that the temperature increases in this isovolumetric process. To state B, you can see it then goes another process. And going from B to C involves a constant pressure. Pressure doesn't change, but the volume does. So it's an isobaric expansion. And how do we know it's an expansion? Well, the volume increases. And going back to our simple engine, if the volume increases, we know that the piston is moving upwards, which means work is being done by the gas. We can also see at this stage that it's going through more isotherms. So the temperature is still increasing as well. So we have go through point B to C, it's an isobaric expansion, and the temperature increases. In state C, we go through another process, and you can see that process goes down towards D. What's happening here? It's another isovolumetric because the volume stays the same. It's going down through the isotherms, so the temperature is decreasing. We get to D, and because it's cyclical, we want to go right back to where we started, so then we go to D to A. The pressure's constant there, so it's an isobaric process. It's losing temperature because it's going down the isotherms. And if it's losing temperature and losing volume, the piston's going down the way, which means work is being done on the gas, and it's compressing. So it's an isobaric compression from D to A. Let's have a look at work done now. If we just look at work done by the gas, then this is the work done by the gas, and then the area underneath the curve is the work done by the gas. So the green shaded area is the work done by the gas. If we now consider the work done on the gas, this is the line here. So the red shaded area is the work done on the gas. And you can see that the work done by the gas is greater than the work done on the gas. What that means is there's a net work done in that system. And it's this network, which is the blue shaded area, that runs the heat engine. So if you have a cyclical process on a PV diagram, instead of looking at the area underneath the curve, you're actually going to have to look at this blue area here, which is the area enclosed by the cycle on the PV diagram. I think it's important for us to actually remind ourselves a little bit more about the engine itself. We're going to start here, stage 1, and that's from A to B. Remember, it's an isovolumetric, the volume stays the same, the temperature is increasing. The gas gets hot because here, fuel is being burned, and there's a transfer of energy from chemical energy to thermal energy. That thermal energy is then added to the system, and the gas gets hot. Of course, as gas heats up, it brings us to step 2. Step 2 is where the gas expands because it's been heated up. And that expansion of the gas causes the piston to move upwards, meaning that work is being done by the gas. Once the piston's at maximum capacity, we move to step 3, where the gas is nice and hot, right? But heat starts to be lost to the surrounding because there's a bigger surface area here. So this surface area allows more heat to be lost to the surroundings. And by that loss of energy means that it gets colder and it starts to compress, which brings us to step 4. And we get the piston moving down, which means work is being done on the gas. This is our PV diagram, and this is how it relates to real life in the piston. Before we move on to the next slide, I want to bring your attention to this heat being lost to the surroundings. It's wasted heat. So it's going to tell you that this heat engine is not fully efficient. And we want to work out how efficient a heat engine is. The thermal efficiency of a heat engine is defined as the ratio of useful work to input energy. And being physicists, we want to create an expression for that. So we take the definition of efficiency and we say the efficiency is equal to useful work over input energy. And by using a little bit of further physics, which you don't really need to know, to be honest. In fact, you don't even need to know this equation. But this gives you an expression for the efficiency of a heat engine. If you don't need to know it, why am I telling you it? But it might speed up some problems in your exams. Let's go to a special case of a cyclical process. It's called the Carnot cycle. As we talked about before, an adiabatic process is when there is no exchange of thermal energy between the system and the surroundings. So we talked about our piston. We know we've got gas in here. This piston is going to go up and down, but it doesn't do it by using any thermal energy. There's no exchange between the surroundings and the system of thermal energy. To do that, heat is transferred at the same temperature as the surroundings. And I'd like us to move towards the PV diagram here and analyse it just as we did the cyclical process before. And we'll start in state A. Gas is in state A and it moves up to state B. To do that, an adiabatic process takes place. You can see the line follows an adiabatic curve. You can see that it increases through the isotherms, so we know the temperature increases, but it does it without the input of any thermal energy. At state B, it then moves on to state C. We can see that the gas increases in volume, which means the piston moves upwards. That means work is done by the gas. It's an isothermal expansion because it goes down one of the isotherms. And that's all we have to say about that. Work done is positive. At state C, it then moves to state D. It does that through an adiabatic process again. It goes down through the isotherms, so the temperature decreases. Again, it does without any loss of thermal energy. At D, back to A to make it a cyclical process. You can see that the volume decreases, means that work is done on the gas, so our work is negative. And I made a mistake here, it's an isothermal compression as well. And compression is used because the volume is decreasing. As before, the area underneath the curve on the work done by the gas is bigger than the area underneath the curve on the work done on the gas. That means that net work is done, and this area here is the area that shows how much work is done by the engine. And actually, this process I'm showing you here is the most efficient heat engine possible. It's the most efficient way of producing work by a heat engine. And this is the equation you need to know for the efficiency of that Carnot cycle. It's the maximum possible efficiency of any heat engine, and it depends only on the difference between the temperatures of the hot and cold parts of the cycle. It may seem a little bit complicated at the moment, but once you start getting questions on this, I assure you it's very, very easy. Let's head to your revision note template. I want you to go to the graph section again. If you haven't got any room, head to the other notes section and draw the cyclical PV graphs for a regular heat engine. And that was the one that looked like that. It was a nice square. And the cyclical graph for the Carnot cycle, and that was the one that had the adiabatic expansion. Like that. Okay? Go to your common definitions section, write down the definition of the Carnot cycle, and write down the expressions for efficiency in the formulae section. Then head to questions 11 and 12 in your knowledge questions. And now we go back to the second law of thermodynamics, which is all about entropy. And we're going to start entropy by considering a thought experiment. I want you to consider this situation here where the number 1 is written. The thought experiment starts with us thinking about a balloon and blowing that balloon up. These little balls represent molecules, and the arrow attached to the ball represents its speed, or is a value of its kinetic energy. You can see that as we start blowing the balloon up, the molecules of the gas flow into the balloon in an orderly fashion through a small opening, all travelling in the same direction with the same speed. It's very orderly. However, you can imagine that after hitting the other side, these molecules are going to start bashing into each other. They're going to start bashing into the wall. They might lose energy, they might gain energy. They're all going to have different directions. They don't have the same energy anymore, and they move around in random motion. Situation 2 is not orderly. It's not orderly, unlike situation 1. And it's this concept of order that brings us to the definition of entropy using something called microstates. Different kinetic energies of each molecule are called microstates. So in situation 1, there's only one microstate because they've all got the same kinetic energy and they're all moving in the same direction. Omega is the number of possible microstates, and the entropy of a system is defined as S equals Kb, which is the Boltzmann constant, times the natural log of this omega. And again, remember, omega is the number of possible microstates. If we head to situation 2, we know that each of these molecules has different kinetic energies. So there could be any number of microstates. Whereas in situation 1, we know the number of microstates is 1. In situation 2, we know that the number of microstates is likely much more than 1, which means that the entropy in situation 2 is likely to be much greater than the entropy in situation 1. That means that entropy in situation 2 is greater than entropy in situation 1. In this case, the entropy increases. It would be extremely unlikely in this thought experiment for the entropy to decrease. And it's this concept of microstates and orderliness that allowed Lord Kelvin to come up with his version of the second law of thermodynamics. And let me talk you through it right now. Let's go to the start of our heat engine. And the start of the heat engine is where we have fuel, it's burned, and that adds heat energy into the system. You can imagine that the entropy at this point, or the orderliness, or the number of microstates is a great many, right? You can imagine that this idea of microstates is big. However, when we get it into the system in situation 2, what's happening is it's causing all these molecules in the piston to go in one direction at the same speed. It appears to be more orderly. Means that the number of microstates is decreased. That suggests that entropy is decreasing. And that kind of goes against what we'd learned about it before. But do you remember we talked about the efficiency of a system, and we talked about how energy is released to the surroundings? And when that happens, that increases the number of microstates. In fact, it increases it more than it decreased in section 2. So if we're looking at the net change in microstates, the net change in microstates is increasing. And that tells us that the net change in microstates is increasing, but means that entropy is increasing. And what Lord Kelvin came up with, he said, it is not possible for a heat engine working in a cycle to absorb thermal energy and transfer all to work. He said some must be released to the surroundings, otherwise the entropy of the system would increase. Let's look at entropy from an energy point of view. Imagine our balloon, it's closed, it's at a temperature, let's say it's, 100 degrees Kelvin. When we add heat to that balloon, then what's going to happen to these molecules is they're going to become more disordered. They're going to go mad, they're going to bounce off the sides, they're going to bounce into each other, they're going to have more kinetic energy. And when heat flows into that body or into that balloon at temperature T, the energy will become more disordered in the body, just as we talked about here. That means if it becomes more disordered, the entropy of the system increases. And when we're looking at thermal energy, there's another expression for entropy that we can use. And that other expression for entropy is the change in entropy is equal to Q over T. And Q is the amount of heat energy that's been applied to the system, and T is the temperature of the body as it increases. The units of entropy are, this is energy, so that's joules. This is temperature, Kelvin, so the units are joules per Kelvin. We now have two expressions for entropy. We have S equals KB ln omega, which is to do with the microstates. And we have the change in S is equal to Q over change in temperature. This allowed Lord Kelvin to come up with his version of the second law of thermodynamics, and this allowed Celsius to come up with his version of the second law of thermodynamics. So Celsius started off with the idea that in any cyclical process, the entropy will either stay the same or increase. And from that, he made two implications. The first implication is that energy has become more spread out. And the second implication is that heat can't spontaneously flow from a cold to a hot object. And with those two implications in mind, he came up with his version of the second law of thermodynamics. And he said, it is not possible for heat to be transferred from a cold body to a warmer one without work being done. And that is his version of the second law of thermodynamics. Please head to your revision note template, write down the two expressions for entropy, write down the Kelvin and Celsius versions of the second law of thermodynamics, and it says questions 11 to 12 here, but it's actually questions 8 to 10 in knowledge questions. Head to questions 8 to 10 in knowledge questions. I think you think that entropy is hard. Try the questions, and I think you'll find it's actually a lot easier than you believe it to be.